Hello students, I want to do a review for this exam because it's complicated. And when I did the review in class, we came up with some problems at the end where I ran out of time. I couldn't explain them very well. So I'm hoping to use this as a means of doing them in a more slow fashion so that my students who saw the lecture can get it, and slow enough that anybody seeing it for the first time will also understand it as well. Let's start. Section 6.1 and 6.2 go together. They both deal with the normal distribution. What do we have? We have z-scores. That was the formula z equals x minus mu divided by sigma. Using the normal table, or more appropriately, the standard normal table. That you should have a printout for you. You can use it on your tests. Calculate areas. So those are the things that I'll expect you to do for that. As far as calculating areas, you should be able to give me any type of an area that I might specify. So using the table, if I give you a z value and I give you the area to the left, I expect for you to use the table and be able to tell me what that area is. Another way, you could have the area going off to the right. So you might, for example, have this area shaded. You should know how to work those kind of things. And then finally, the last type we can have is something like this, where it's trapped between two values. And z1 and z2 can actually be on the same side of 0 if the problem calls for it. There's nothing that prevents it from possibly happening. So let's do an example here. I plan on giving you one of each kinds of these graphs, so you could count on 3 of them. And I think I'm going to do about 5 points apiece, so this represents 15 points of your test. Let's do an example. Let's calculate the area of the shaded region. This one is pretty straightforward. You should by now be able to go into the table and get me this value. You should know how to look them up by now. If you come to the negative section of the table, I have negative 1.12. So I'm in this row here where I got my mouse pointer, negative 1.1. There's negative 1.10, 1.11, and negative 1.12. So given the z value, you should be able to do these. The next kind, let's put z on the other side of 0 and go positive. Actually, no, I'll tell you what, let's do 1.12 here. That, of course, you can get right from the table. This time you just look up positive 1.12. And 86864, 86864. I can kind of check myself too. If I take this number here and add it to this number here, I should get an area equal to 1, which it looks like that does add up to be that. Next, on another type that you could encounter let's put negative 1.95 here, and then shade this region. So shading to the right is a little bit different. Now what we always have done is we found the area in there. So let me go find the area to the left of negative 1.95. See, 0, 1, 2, 3, 4, 5. So 0.02559. If I want this area, then I can subtract that from 1. .97441. Another way you could have done it is you could have looked up positive 1.95 in the table if you're savvy enough to do that. Look what the table is for, where is it at? The positive 1.95. If I go to positive 1.95, there it is, our 9744. So I was able to check myself. And that's something that you can do as well. If I ask you to find this area, you could look up negative 1.95, or you could look up this area out here. Either way you get it, you'll get 0.02559. Now for these, I typically will look up that in the table directly, negative 0.97. For this other one, you could look up negative 1.69 if you want to get it directly. And then to get the middle part, subtract those two numbers from 1. Now these are using the table directly. You should also be able to tell me a z-value if I tell you an area. As an example of that, if I give you something like that and expect you to find the z-value, then you go back into the table and try to find 0.95 in that table. Here's the relevant section of the table. I see the 0.95 is sandwiched between this value and this value. So that is from the row 1.6, 4, or 5. So you know how I go 0.045. And so this z-value is 1.645. So I imagine I'll probably give you about 3 of these as well. One that has shadings to the left, to the right, and then between. So you'll have to handle those situations. And then z-scores, just a calculation of the z-scores. For example, If I give you x equals 5, mu equals 1, and sigma equals 2, then the z-score is simply x minus mu over sigma. The x is 5 minus 1 over 2, and that will equal 2. So I'll just give you something as simple as this. So I imagine probably just 1, 2 at the most. So I'm looking at, so far, all of the questions that I would have asked so far would have been 5-point questions. So I think we're at 6 or 7 right now, probably 7 questions, about 35 points. Most of the rest of the problems are going to be actually doing applied problems. This one comes out of the homework for 6.2. I don't care about part A of this problem. I'm more interested in B and C. Suppose the distance of fly balls hit to the outfield in baseball is normally distributed with a mean of 250. That's our mu. And a standard deviation of 50. That's sigma. If one fly ball is randomly chosen from this distribution, what is the probability that the ball traveled fewer than 220 feet? So let me draw a picture of this situation. Here, the center of it is 250. And we want to know what percentage was less than, or probability was less than 220. So since they said less than, it's to the left. Let's get a z-score. Z equals x minus mu divided by sigma. The x is 220. And you'll end up with negative 0.6. So the corresponding standard normal distribution table will look, or graph will look like this. And then we can look that directly up in the table. So there's a pretty straightforward one. A problem like this would probably be worth 10 points. And then the 80th percentile is probably worth 10 points as well. The reason why is you have to do multiple steps. So setting up the picture, doing the z, I'm not sure, these might be 5, but finding the z value based on the area, that's probably going to be worth 10 points because those are harder problems. So in part C, let me copy it, what they said here. All right, so this time what we're looking for is something like this. We know the center is at 250. But the 80th percentile, I know is going to be around here somewhere. We want 80% inside of there. So let me go ahead and pull up the table and see if I can find 0.8 on the table. Here's the relevant part of the table. I want to find 0.80 and it's not exactly on here. So there, it's bigger than that but smaller than that. So what do we have here? This is 0.845, so I'm going to do 0.045. So this, well, I got ahead of myself. This table only works with the standard normal distribution. So I'm going to use z equals 0.845. And then to go get x back, we need to use this. Z equals 0.845. I'm going to replace z with its formula. Let me put in my mu and my sigma. We know those. It's at this stage that I like to slide a 1 underneath of the decimal, so it facilitates cross multiplication. Finally, to get x, add 250 to both sides, 292.25. And at this stage, I'm going to put in the units. This it constitutes all the types of problems that I want you to be able to do in section 6.1 and 6.2. The next grouping of problems. So in 7.1, we were doing sample means. 7.2, sample sums. And then 7.3 was just a mixture of these two things. The formulas that we'll need here, Z. Let's start with 7.1, sample means. Z equals, since we're talking about sample means, a sample mean minus mu sub x bar divided by sigma sub x bar. Notice the notation here. Mu sub x bar is going to just equal mu, the population mean. Sigma of x bar is going to equal sigma divided by the square root of n. N, of course, is the sample size. To illustrate this, let me get rid of part A and let me write down what we know. 250 is my mean, 50 is my sigma, 49 is my n. So let me get these things in here. Mu sub x bar is going to just be mu, so that's 250. And then sigma sub x bar is sigma divided by the square root of n. Sigma is 50, square root of 49. This is what I got for my sigma sub x. What is the probability that the 40 balls traveled an average of 240 feet? All right, so let me get a picture of this. This 250 is because our mu sub x is 250. And we want less than 240 feet. So 240, let me put about here. And then we're going to shade this way with it. So let me go ahead and get my values for that. Here it's x bar minus mu of x bar divided by sigma of x bar. I now have all those numbers. 240 minus, where's this guy here? 250 divided by 7.14286. Well, rounding gives me 1.4 here. Very nice. Now I can go to my standard normal table. And go look up 1.4 in it. Gotta be careful. Let me put it over here too. I missed it in two places. In terms of percentage, that's just a hair over 8%. Part C was to find the 80th percentile. So what's that going to look like? The 80th percentile has to be over here somewhere. So to get that x value, I first got to go through z. Fortunately, we did it in the last problem. So I know that z is equal to 0.845. Now let me replace z with its formula. This is where I slide a 1 underneath of that number. Cross multiply. And finally add 250 to finish it off. And that should probably be in feet. In section 7.2, we looked at sums. Here, our z-score looked something like this. It looks sum of x minus mu, the sum of x, divided by sigma sub of x. And here we have mu sigma x equals to n times mu, and sigma of sum of x is equal to the square root of n times sigma. First thing I would do here is start computing the things that I need. Let's start with mu sub sum of x. That equals n times mu. Our n here is 49, and mu is 250. That's 12,250. Our sigma sub sum of x equals the square root of n times sigma. That's the square root of 49 times 50. Square root of 49 is 7. Now we're ready to start working the problems. Part A, what's the probability that the sum of this sample is more than 11,515? Now you're remembering you're dealing with sums here. So your mean that you're going to use here is this guy. That'll be the center of your curve. And we want the probability that the sum of this sample is more than 11,515. So let me put that here. So we want to find this area then. Let's get our z-score. Let me put in my numbers. The sum of x, that's the 11,515. The mu sub sum of x is the 12,250. Divided by 350. Negative 2.1. So now I transport it to the standard normal distribution. I'll go to the table to find out the area of that region. 0.01786. And then we'll subtract that from 1. And there you go. The second part was to find the 80th percentile. All right, let's draw a picture of the initial situation. Here, since we're talking about sums, I have 12,250 here. The 80th percentile will be some sort of a sum. We'll call it that. Go to the z-score. We've done this one several times by now. I know it's to be 0.845. And then so we'll go and try to figure out the sum of x. That's the unknown quantity here. Z equals 0.845. On the other hand, the formula for z is the sum of x minus mu sum of x divided by sigma sum of x. And let me put in my numbers. That mu sub sigma x, what was that one? Go back up here. Of course, 12,250. I didn't need to go up there. All I had to do was really look here to get that. Sigma, though, is a little bit more different. That's 350. Put 845 over 1. Now this thing right here, this is also known as the error. Somewhere you need to know that the error for things is z times some sigma of some sort. I don't know which sigma to put, so I'll put a sigma with a question mark. That's always, whatever the sigma you're dealing with is, you multiply that by the positive z value and you'll get the error. And that's also just a computation that happens to come about while doing these problems. Now I'll add 12,250 to finish this off. And there's our 80th percentile score. These are the things you can be expected to do in section 7.1, 7.2. 7.3 is just doing problems from 7.1 and 2 in a mixed, I don't want to say mixed, yeah, they've mixed them up. And you have to decide which to use. So altogether, we have 3 things so far. We have, if I draw on one item at random from a population, you have a formula for that. If I grab a sample and take its mean, I have formulas for that. If I have a sample and take its sum, I have formulas for that. (8.1) we did confidence intervals for the mean. And it looks like this. E in all types Since I'm dealing with the means, the error here will be whatever z value I get times sigma sub x bar. So that'll be my error for this particular time here. We also need to find out the size of n. So from this calculation here, you don't have to follow along with this if you don't want to. I'm just doing the steps to show you how we get the equation. I'm going to cross multiply here. Then I'm going to square everything. So in order to do this, you'll need to know the z value, you'll need to know the population standard deviation, and you'll have to be given an error to work with. So these are the formulas that we're going to be using. Let's put stars by them. There's that one, and there's that one. And always don't forget the z values here whenever you're dealing with the mean. All right, here's an example. We have announcements for 84 upcoming engineering conferences were randomly picked from a stack of IEEE Spectrum magazines. Fine. So we have a sample size of 84. The mean length of the conference was 3.94 days. And the standard deviation is 1.28 days. So we're going to use that for our sigma, and this will be our mu. I don't care about this part of the problem here. But what I am interested in is part B, normal, because you're looking at sample means. And they want you to construct a 95% confidence interval. So here's how that should look. The center of this thing is at 3.94. And we want a 95% confidence interval. Since we're talking about means, they look like this. I want 95% of the data trapped between those two values. That means, in particular, that's 2.5% out there and 2.5% out there. So the first thing you do is get the z values so you can work your way backwards. Fortunately, in here, it works really nicely. You're going to have a negative z and a positive z. So, and the 95% will be in here. We would go and try to find 0.025 in the table. Let me see how hard that is. Here's the relevant portion of the table. I saw 0.025 on it. Here, it's right here. It's actually in the table. So that's negative 1.96. That would make this one 1.96. Now let's go about getting our x1 and x2 values. I'll start with the left one. I'll come back to that after I write my first equation. Here on the left we have z equals negative 1.96. That's the same as x bar minus mu sub x bar divided by sigma sub x bar equals negative 1.96. Mu sub x bar is 3.94. Sigma sub x bar, what were you, sigma? I don't think there it is, 1.28. Well, I don't think I calculated sigma at all, actually. Nope, let me get that one. For this, you're going to get sigma over the square root of n. Sigma was 1.28 divided by the square root of 84. So now that I got that, 0.13966 equals negative 1.96 over 1. Cross multiply. Let me keep consistent with my notation here. Now, remember, the easier one to do is the second one, because you can come right down to this spot, and we have x2 minus 3.94 is equal to 0.27373. And then add 3.94 to each of these equations. $3.66627 for that one. So I've got my interval then. Confidence interval equals 3.66627, comma, 4.21373. Here's another example. So I gave the formula for calculating n. This 2.5%, that means E equals 0.025. Your n goes by the formula z squared times sigma sigma squared actually, and then E squared down here. Everything is squared. The z, that was the same z from the last problem. We're still working a 95% confidence interval. So I'll have 1.96 squared. The sigma, let me go and recheck what that was. Standard deviation is 1.28, so I have 1.28 squared. And then finally, the error. Here I get 10,070.5, which you'll have to round up to 10,071. (8.3) had to deal with proportions. And we did exactly the same things as in 8.1. We did confidence intervals. And here they'll look like this. Where E, of course, is the error. And then the size of n. All right, in this problem we have Stanford University conducted a study of whether running is healthy for men and women over age 50. During the first 8 years of the study, 1.5% of the 451 members of the 50 Plus Fitness Association died. Well, then we have 451 is the size of our sample. 1.5% then is the proportion, so we'll call that P prime. Remember, the proportion of the sample is called P prime. Notice they didn't tell us how many members died. If they had told us, say, like 5 people had died, you would take 5 would be your X, the number of successes, and you would divide it by 451. I'm not exactly sure. Just out of curiosity, let me see how many people that was that died. Well, 6.7 people died. These are rounded numbers. All I care about is that's what P prime is. I don't really care about part A. Part B, you're going to use normal for everything. The population proportions, or the proportions themselves, those numbers form a normal distribution when n is big enough. Before I do that, let me get our information down here. I've already got P prime. I don't need to do anything with that. I don't exactly know what to call this, but let's call it sigma sub P. Your book doesn't have a notation for this. And this is equal to the square root of P prime times 1 minus P prime divided by n. So let me get that information there. Our P prime is the 0.015. And then 1 minus that is 0.985. And I'm going to divide by 451. It's good to have these numbers out front. Now let me draw a picture of the situation here. Here our center is 0.015. What are they trying to get us to do? This is part C is what I'm going to do here. We want a 97% confidence interval. So what are these? I'm not exactly sure what to call these things. Let's just call it X1. I guess we can call it, maybe call it like this, P1 and P2. How's that? I like that better. Because these are proportions anyways. Let's put 97% in here. That means out there is 1.5%, and out here is 1.5%. So we'll go to the standard normal table. Will look something like this. 97% will be trapped between those two z values. So I'll go and look up 0.015 in the table to get that particular z value. Here's the relevant section of the table. I'm looking for 0.015. I think it's somewhere in this table. It's actually right there. So we have negative 2.17 there. That makes this 2.17. Now let me get my P1 and P2. So we have Z equals negative 2.17. Z equals P prime minus P divided by, and in here I want to put P prime times 1 minus P prime slash n. And that equals negative 2.17. Let me put in my numbers. That bottom one we calculated, it's up there somewhere. One of the first things I did. 0.00572. So I'll put that over 1. Cross multiply. And then I'll add 0.015 to both sides. Now the other one's going to be a lot easier. The one that starts out as z equals 2.17. You can come right down to here, and this time we have p prime minus 0.015 equals negative, I'm sorry, this time it'll be positive. I can't copy that much of it. 0.01241, and then I'll add 0.015 to both sides. So our confidence interval then will equal 0.00259 up to 0.02741. Now, if you go to percentages, it may make this might look better as percentages, but I'm not going to require that you put your answers in any particular format. So there's our estimate, anywhere from a little more than 0.25% to 2 3/4%. All right, this is the last of the types of problems that you can expect on the test. Assuming the same details as the last problem, in the last problem we had a p prime, we had a 97% confidence interval. So let me get what we had here. At p prime was equal to 0.015. What else did I need there? Well, they're giving me the error. I think we got the 1.9. What was the z value? 2.17. I don't know whether to call it sigma sub p or sigma sub p prime. What was that equal to? 0.00572. Actually, that's going to change. Back here, I think I can get the formula here. We have, if we can remember correctly, size n equals z squared times sigma squared. That's the population standard deviation. And then we have e squared. So z from the last problem was 2.17. Sigma equals p prime times 1 minus p prime. And actually not that, actually it's the square root of that. If you'll remember that, this is the population for the binomial coefficients or binomial properties, I guess. So let me rewrite this. Before I put in the numbers, let me get this back here. We'll have z squared. When I square sigma, I'm going to get p prime times 1 minus p prime, and I'm going to divide by e squared. All right, so I still got my z, which is 2.17 squared. P prime is 0.015. 1 minus p prime is 0.985. And in the denominator, I'm going to have 0.01 squared. Of course, as usual, you want to round up. N will equal 696.